Hello, everyone. I am Sewon Lee from Seoul National University, South Korea, and I'm here to present our recent work on recommender systems titled Mixture of Conditional Attention for Multimodal Fusion in Sequential Recommendation. Let's first start with what recommender systems are. You can think of it as a filter that suggests items that are most relevant to the user. So it's useful when a user wants to choose an item from an overwhelming number of items provided by the system. And sequential recommendation has especially gained attention for its ability to capture the evolving user preferences over time. The goal here is to predict what item the user will consume next, given their interaction history or sequence. For example, consider a user who used to watch animated films like Frozen before, but later watches Iron Man or Captain America, like superhero films more. And considering this change in taste, we can predict that this user is more likely to watch The Avengers next rather than Frozen 2. And recently, the transformer-based models using self-attention has shown strong performance by effectively capturing the relationships between sequence items. And in transformer-based recommenders, we first obtain a sequence of item embeddings, which is then passed through the transformer layer. The output of the last item is commonly used as the final user sequence representation. And then the model recommends the top n items whose embeddings are most similar to this user embedding. And many recent approaches also leverage multimodal content, such as poster images or titles, beyond just item IDs, in order to better represent items and user preferences. So here, now we want to add the multimodal content features, but how can we do that? One naive way is to feed all modality features into the transformer, treating everything as queries, keys, and values. The right figure here is the attention pattern, where the different colors, like the gray, yellow, or green, indicate each modality. But there is a problem with this approach, that this vastly expands the search space, causing significant computational overhead and makes model training more complicated. And to deal with this, previous methods have proposed two main strategies. First, the early and late fusion, each specifying which tokens should serve as query keys or values, instead of using everything. First, early fusion assumes that features within the same item are highly correlated. So we combine them, for example, ID, text, and image, into a single item embedding, and then feed it to the transformer. On the other hand, late fusion focuses on alignment within each modality. It first processes each modality, like all image features or all text features of sequence items, through their own transformers. And then the outputs of the last items across these modalities are combined into the final user representation. But both early and late fusion rely heavily on these predefined rules. And while these fixed rules can help guide the training process, they limit the model's ability to flexibly explore the cross-model relationships in the data. Now, what if we remove these fixed rules? How about letting the model learn how to choose which tokens to act as query keys and values so that they can flexibly learn the diverse cross-model patterns directly from the data? To this end, we propose mixture of conditional attention, or MoCA. Its main mechanism can be divided into two parts, the conditional attention and the mixture of experts approach. First, in conditional attention, we focus only on the most relevant features aligned with the user's intent and apply attention only within them, instead of using fixed rules. To do so, the model first has to learn to identify these relevant tokens to serve as query keys or values. Specifically, we apply a learnable projection to all of the input tokens, so item feature embeddings here, and select the top K tokens among them. We perform this token selection twice, first for tokens that require additional information, the queries, and second for tokens that provide additional information, the keys and values. And then we perform attention using only these selected queries and keys values. This selective focus allows the model to perform more efficient and meaningful attention operations. And to reflect diverse user preferences, we extend this idea with a mixture of experts approach. Here, multiple experts independently perform conditional attention, and their outputs are aggregated. This allows the model to learn diverse and flexible attention patterns, adaptively capturing the various preferences of users. Here's the overall architecture, which consists of three main components. First, an embedding module to get item feature embeddings. A second, a sequence encoding module that generates user sequence representation. And third, a prediction module for final recommendation. First, let's look at the embedding module. It produces item feature embeddings for each modality feature of each item within a user sequence. And it uses a modality-specific encoder, such as ID, text, or visual encoder. And importantly, all modality features of all items are preserved and used directly as inputs to the attention without any aggregation. And to ensure consistency across the embedding spaces of different modalities, we introduce the modality alignment loss, L-align. And here we use the ID embedding as the anchor and apply contrastive loss across all the modalities. And this encourages the model to pull together the feature embeddings of the same items, across modalities, while pushing apart embeddings from different items. Next, the sequence encoding module generates user sequence representation based on these item feature embeddings. Here, MoCA operation is applied twice, first in feature level and second in item level. First, we perform feature level conditional attention across all modality features of all items. And this helps the model discover meaningful cross-model relationships. And then we aggregate these into item embeddings and apply MoCA again at the item level, learning how sequence items relate to each other. And the final user representation is obtained from the last item's output. And third, we get the relevant scores between users and items by the dot product between the sequence embedding and item ID embeddings. And we finally recommend the top N items with the highest scores. And we train MoCA with two loss terms. First, the main recommendation loss uses binary cross entropy loss. And notably, we use a novel soft label strategy here. And most traditional methods only use the immediate next item as the label. So 1 for this next item, but 0 for the future items beyond that. But instead of this, we assign decaying weights, decaying labels to these subsequent items as well, assuming that user might also be interested in subsequent items beyond just an immediate next one. And the overall loss is the weighted sum of this main recommendation loss and the modality alignment loss introduced in the embedding module. Moving on to the experiments part, we evaluate MoCA on real-world datasets from Amazon reviews and Movie Lens dataset. For content features, we use product image or movie trailers for visual input, and product title plus description or movie synopsis for textual input. And we use the widely used leave one out protocol, using the most recent interaction for testing, the second most for validation, and the rest for training. And this table compares MoCA with both ID-based and the multimodal content-based sequential recommenders. We report the performance using two metrics, the heat rate, HR, and NDCG, both measuring the accuracy of recommendation. And NDCG especially considers the recommendation ranking or position as well. And the higher, the better for both. Here, we can see that content-based models generally outperform the ID-only models, demonstrating the benefit of using content features. And among them, our model, MoCA, consistently achieves the best performance. Next is the ablation studies. Here, we demonstrate the effectiveness of using MoCA operation by replacing it with full attention or no attention at all, which led to a clear performance drop. And next, we analyze our soft label strategy during training. Not using it at all results in worse performance than the peak, showing the effectiveness of modeling extended user interest. Setting the decay rate to 1 corresponds to giving the same weight to all of the feature items without considering the sequence order, which significantly degrades performance. And this indicates the importance of sequential modeling. And for the modality alignment loss, removing it by setting loss weight to 0 performed the worst, which demonstrates the importance of modality alignment. So to summarize, we propose MoCA, a novel framework that allows the model to flexibly focus on features aligned with various user preferences without relying on fixed rules. And this is the end of my presentation. Thank you for listening.